So good morning, everyone. Still not known. So we are very happy to have Subhasish with us today. Apparently, Subhasish has visited SNO Center before. Somehow it's not in my memory. But Subhasish is a person whose research expertise is mostly with the electronic structure calculation and mostly focusing on strong correlation method. And he did his master's from IIT Madras. So was he his classmate? I see. So then he moved to US and did his PhD from Michigan Technical University, and then he did two postdoc, one in Yale IBM, another in Rutgers, where he got into DMFT with Christian Howley, and so please. I believe that his talk will give rise to several possible collaborations.
Okay, so good morning, everyone.
Maybe you need the microphone.
Microphone is there.
Oh, okay.
Is it working?
Yeah.
So, yeah, so it's a great pleasure to be here, and thanks for the invitation and for introduction. So, today I'm going to talk about first principle investigation on strongly correlated materials based on beyond DFT methods. So I started this new position in West Virginia. Most of my work was done, last fall, as an assistant professor. Most of my work that I'm going to show here was actually done when I was a postdoc at Rutgers and before at Yale. So let me just give a little bit outline of what I'm going to talk about. So I'll give you a very general introduction. I know many of you know about electronic structure and why it's important and how it was done historically. Then I'll jump into two very popular methods. One is called GW, and is called DFT plus GMMP. And I'll just make a quick route to my work at Yale about high scalable software development in GW. And then mostly I'll be talking about benchmarking this beyond DFT methods. And ultimately, can we find out a method that is working? And can we even build databases based on those methods, etc. And finally, I'll talk about so most of the talk is first half we will see the spectral properties of in the investigation of spectral properties. Then I'll also talk about some structural and vibrational properties. So most of these beyond DFT methods are famous for spectral properties, but is it possible also for structural or vibrational properties? And you'll see how it comes. So if you look at the construction of solid state physics, you have some great physicists like Landau and Fermi. So what they taught us is like why things happen in nature, right? Where in material, given material. What they have not taught us is which material is going to show a given property. Okay, and that kind of things change with the invention of density functional theory by Walter Kohn is the paradigm. Okay, that we can actually design material, predict material. You tell me a material, and I can tell you the electronic structure, magnetic properties, vibrational property, or even we can predict material ahead of experiment. So this is a new era that we know. So what we are going to in next decade is like, can we build a database and then use artificial intelligence to actually predict materials? Okay, so why materials designing works? Because the basic ingredients are all hidden in our periodic table. We are only our interest is that those elements aggregated together and form a phase. And if you remember one of the Marvel's movies, that the hero is actually picking up elements from the periodic table and making his own material. Okay. So basic input for a DFT calculation is like which atom you want to work on, and then I can give you all this sort of exciting property. And using artificial intelligence or data science, the first step is to have the data. Meaning, first step, you have to build the database. And there are databases kind of popular last 10 years or so. Few of them in the US, some of them in the Europe. One of the popular databases is a materials project database that was built with the FT. Okay. Now, this has almost 100,000, more than 100,000 compounds with millions of properties. Many of them are not even synthesized. And this has kind of changed the culture of data sharing, which was lacking in condensed matter. And it is also a playground for your own machine learning model for this database. But if you look at carefully at this, any of these databases, most of the time you will find that, very often you will find that this database would predict incorrect results just because density function theory was used. For example, in iron oxide and cobalt oxide, they are insulator. If you do a DFT calculation, you will show a metal. And the vice versa is also true. So it is something that it does not occur only, suddenly few instances. And we can actually categorize two types of material. One is weakly correlated system, as you know, where electrons motion is influenced only by the Pauli exclusion principle, and mean field approximation such as DFT is good. And other is strongly correlated material. Then we can categorize like if DFT does not work, maybe this is strongly correlated material because this kind of averaging will not work. Now, just to give a pictorial view of what is weakly correlated system or a strongly correlated system. Strongly correlated system is one motion is completely dictated by or somehow dictated by others' motion, and it happens also in the material where the electron's mass gets really large. So these are not just a concept; these are actually technologically relevant materials. We have to be quite serious of getting them accurately understood. So, for example, photovoltaics or high temperature superconductors, they are the examples of strongly correlated material. Now, how do we deal with it? So we have the standard model, which is the density function theory. The way it works, just like in one line, we know that every point in the crystal is mapped with electron gas problem to the density in local density approximation and through the density and the gradient of density in the GGAs. So if it is mapped with with electron gas problem, and then going beyond here, you have GW, and we're going to talk about detail, and DFT plus DMFT. So in DFT, in GW, you start with DFT, and then you kind of correct it by parting the system to the first order or second order, depends on where you want to stop. In DMFT, we can take almost all higher order Feynman diagram, but the thing is it is locally on some atom, whereas in GW it is for the entire system. Okay, so we're going to see this kind of methods in detail, but this is how this methodology works. So things starts with DFT and then you correct them. So little bit about GW equation. So in DFT we have this we have this Cohen-Shum equation where you have this kinetic energy, ionic potential, Hartree potential, and exchange correlation, and this is single particle equation, and this is also local, so it depends only on Earth. In GW, we follow a very similar looking equation for Dyson equation. The first three terms are precisely the same, but then we have a self energy which is non-local. Not only that, it also depends on the energy of the frequency. So all the ignorance are kind of put together here in this one term connected correlation. And in GW, we approximate this self energy in terms of Green's function and the W's. Now, if you take any insulator or a semiconductor, you do DFT calculation, you will see that it is going to underestimate the band gap a lot because it's a ground state theory, and GW is kind of corrects really well. But it also comes with a lot of difficulties because GW calculation has it's very costly.
So just one question.
Right.
So of course, the GW is being non-local.
Right.
You do take into account the independence of the
Right.
certificate,
Right.
but frequency dependence is somewhat restricted.
Right.
So in these calculations, how much of the frequency dependence is taken?
So
I mean,
this,
all these calculations GW primarily people show are for the semiconductors.
right.
They never apply it to the transition technology.
You will see why. That's what you are going to see. They never apply. And why? That's what we need a benchmark, and I'm going to show it to you.
Okay.
That there's limitation of GW. Okay, it's actually what you're saying exactly right. But this frequency dependence thing is a key point that is taken care really well in the MFT, and we're going to see like head-to-head comparison here, GW and the MFT. So GFT, it scales with n cube. That means number of atoms or unit cell it scales with n cube. GW scales with n to the power 4. But really, it takes almost one order of magnitude higher. So if you have a big system like model system, it's almost impossible to do GW calculation. Or suppose you have a system with some molecule attaching with some nanowires and this kind of stuff, then GW calculation will be very difficult and almost impossible because you do not have a software to deal with it. Even if I give a big computer, you cannot use it because there is no high scalable software. And that was the goal of the project while I was at Yale, and it was collaborated with IBM. That time with Glenn Martina. So we developed this code, Open Atom GW. So there's already existing Open Atom DFT software. We included GW in it. So what we did is we improved a lot of algorithms, and we collaborated with some computer scientists from Champaign, and everything was written in a very sophisticated way using Charm++ parallelization techniques using instead of just MPIs. So this is kind of technical, but this is the summary of the results of the scaling results. So here I'm showing the computing time of polarizability, which is the main non-local part of the calculation and takes almost 70 to 80% of the time. And the system is silicon, but with hundreds of atoms and almost 2,000 bands. So we need to use the polarization techniques, and we have to truncate it somewhere. Non-occupied bands are like around 2,000, and then we're comparing with another software, Bartlett GW, which is written in the reciprocal space. We have written everything for the polarizability in the real space. And you can see two things. One, that every time we're taking less time. And two, it is going almost straight line till 1,000 nodes. And each node has a 60 processor. So 60,000 processor is going to scale. But whereas the other software, and this is one of the best software in GW, kind of saturates. So now, given a big system, you can actually compute.
So the scaling,
Yeah.
better scaling of your open source.
Right.
So that is only the better coding, or
No.
is it also some?
So physics is there, of
Physics.
course. Yes. So I have some slide I can show it in the
Okay,
later.
no
But yeah, so there are
So
some.
there is also some physics.
Of course, the algorithm is, so what we did is it's written in R space, and you see that we have to always balance whether we compute something in real space or in reciprocal space. Some properties are good at reciprocal, some properties not. We had made this so this choice, because we are building this code from scratch and we have the ability to choice. Now, Bartlett GW was kind of using all the conventional way of reciprocal space. Everything was in non-reciprocal space. And so this is the main reason. And then you are going to see even more, some insight I'm going to show you then, maybe after the talk. So this is kind of work that I did for developing open source software for GW calculation, and you will see what Professor Shah was saying, that was hinting that GW might fail for the strong, very strongly correlated limit, and it was never applied. It was only occasionally applied to very strongly correlated material, because we're seeing that if you go beyond, if you're going for a strong correlation length, then you need to go to a model Hamiltonian, Harvard plus Harvard Hamiltonian, or DFT plus JNFT. But the main problem in DFT plus U, there are two issues. Yes, you can solve certain problems with DFT plus U, which was not solved in DFT. First of all, the U is a tuning parameter and is extremely sensitive from material to material. And one can compute U from first principle, but still it is very sensitive. And the other issue is it's actually a band field. You are not moving away from the band field. So we need to go really beyond band field. And that is where we need to go for the dynamical mean field theory. I'm going to give a very short description about how it works. So suppose you have a spin system. You have one spin surrounded by all neighboring spins. If the spins are, the number of neighbors are kind of infinite, then you can turn this to a many-body problem where you have effective interaction, mean field interaction with one spin, kind of seeing average of the rest of the spin. Okay. In DMFT, a many-body problem was introduced by Ravi Kotliar and Anton Georges. They have converted a many electron problem into an impurity problem, where this impurity atom is seeing the rest of the electrons, which are treated as a non-interacting bar, and they are connected through strong hybridization function to a very strong frequency dependence. So this was the idea of dynamical mean field theory. So it is not following, solving Schrodinger or Dirac Dyson equation. It has a different take. It solves impurity problem. So now it has to also marry with DFT to actually work for a real material. And this is a code that was developed again at Rutgers by Christian College, where this DFT part was done using LFEW or all electron beam method, and then the DMFT was done. The many-body problem was actually is done using CPQMC, very sophisticated techniques. And if you want to really compare with DFT, so as I was saying, in DFT you are kind of mapping every point in the real crystal to electron gas problem to density. But in DFT plus DMFT, you can think about you're mapping every atom to an electron bar, where impurity is talking with the electron bar, but the non-interacting electron to the hybridization function, which is a strongly frequency dependent. But in reality, it is quite complicated than just DFT. It is multi-level, self-consistent loop, etc., and it is solved in the imaginary axis. One important thing for the expert in the audience that we do not use any downfolding. So although DFT is kind of a model Hamiltonian approach, but typically is done, it is downfolded to a Wiener orbital and then solved. But since we use this LFEW method, where you do not need another like Wiener orbital project, we can project it into the atomic orbital, and we do not need any downfolding.
Do calculate the projectors?
Of course, yes, we do calculate, but we do not go to outside space, and that gives a lot of freedom. And the freedom is now really challenged in this moment, like how to compute force. If you project in the Wiener orbital, force will be very tricky. Total energy we can get, and that is also a kind of a big advantage of no downfolding. Another advantage is the double counting. You can write a complete theory using this projecting techniques, where we are using the exact double counting, because there is also you take into account some extent correlation, and then you also have extent correlation. Yeah, there is double counting, and this is a big issue in the beginning. So now we have improved these techniques. So no downfolding is the trick here. It also has some demerits. For example, since this is like really all electron problem, if you have a big system, then it is kind of tough. Only because the DFT is tough, not the DMFT. You're going to see that it scales very well. So now we have discussed DW and DMFT. Now the thing is, how do they compare? I give a given problem, which one is the best? The DW or DFT plus DMFT. And we also have some other beyond DFT method, meta GGAs and hybrid. They're kind of still in the mean field approximation, but we can still consider a hybrid functional. It's not a conventional DFT. And then we put together all this method saying that these are the beyond DFT method, and we're going to compute.
One comment. Problem is possibly there is no single method which can address all the elements of the periodic table.
Yes, absolutely.
Started with that motivation.
Right,
That's the problem.
That's the problem because these are all approximated methods. None of them are exact methods. There's some limit to work or not. So that's why we need to benchmark, and that's why that's what we did. Like we're going to do a head-to-head comparison for a given material, and we're going to tell which method is going to perform better, and then compare it with the experiment, and then importantly, that we have to make it available, publicly available for reproducing, and also it can be really helpful for the experimentalist also to access the data. With that in mind, we started building this database called Jarvis Beyond DFT database. We hosted at NIST. So Jarvis is a DFT database, this acronym. So we have added another leg. It's called Beyond DFT. So if you go to this, so it's kind of a review article that we wrote about the Jarvis. But if you go to this website, then you can access all this data, and where you can interactively just select atoms from periodic table, go to the element, and then you can see compare how DMFT, BT, and meta GGAs compare with each other. Okay. Now let me tell you a little bit about the construction of this database. So the structure were taken from ICSD, which is experimental structure. Because sometimes we've seen that DFT structures are not good, so we should not be building a database on the wrong structure. All these methods is DWDM, it starts with DFT as I was saying. So the DFT part for all these methods are same basis, and this is described in Win2K. So we've taken meta GGS is the modified Baker junction, hybrid DFT is built to live, and for GW, using all electron, we initially started with this code, the gap code, but then we found that it does not work for metals. So we have to actually build our own code for PyGW. It's written in Python, and it's good for metal as well, because we now understand what happened. And it is actually very rare to see metals in GW. A lot of difficulties.
You just use G0W.
Yes, most of the time, but sometimes also G0W, GW not. But then if you go to this, this self-consistent GW, there's a lot of other problems. Like sometimes it even works worse, sometimes works better. And then the problem also is there in the self-consistency, and this G0W0 is kind of standard, or GW0. So there's a lot of work going on, also going beyond this truncation. Now, again, the starting point is always LDA for all these methods, but we're not tuned the starting point, and then we're going to see how it works. With DMFT, with GW, with meta GGA, with hybrid functional. The first set of materials that we investigated is binary transition metal oxide, because this kind of playground for strong network materials. namely iron oxide, cobalt oxide, manganese oxide, nickel oxide, they have a very similar structure. But somehow you'll see that and they all they have antiferromagnetic order, second antiferromagnetic order, and again this is the experimental lattice parameters are considered. If you take manganese oxide and just the GGA, the DFT, then you'll see this blue part is from the experiment, the photo emission and the inverse photo emission. We compare with GGA, it's going to give a small gap. You can fix it with GGA plus U, but you have to be precise for the value of U. If you just do meta GGA that hybrid, they actually can open up the gap, and they're pretty good actually. For GW also they avoid open up the gap, and same as in DMFT comparison is really well. Now, similar structure, manganese oxide. If you apply the same thing as cobalt oxide, so if you want to make a model is not going to work because you just replace manganese with cobalt. You'll see that it's not going to work because GTA is going to give you metal. So is meta GTA, and you see only hybrid functional uh, works well, and DMFT. Again, DMFT was pretty good for the photo emission and inverse photo emission.
Yeah, you were showing nickel oxide.
Yeah,
Where
yeah.
is this satellite?
Yeah, right. So turns out that if you compare, sorry, in the scale because of the Windows conversion. So if you compare the RPS, then you see that there are lots of extra band that you can see in hybrid that you do not see in the experiment. The experiment was done by CXN quite a long ago. It's a red dot. These days you can get RPS as uh, really resolved, and you can get the RPS like the plot in green, which I'm showing for geometry. So back in those days, these are like dots. So now you can see there was no extra band in the RPS. So RPS would work better. DMFT would work really well for the RPS. Now, since this is here, DMFT can actually consider paramagnetic phase. So we can actually compare between paramagnetic and antiparamagnetic phase. So for the cobalt oxide, if you see paramagnetic and antiparamagnetic phase, the gap size remains unchanged. We're going.
I still went back to nickel oxide.
Right.
I remember from the old time,
Right.
they have to use really GW glass DMFT. They made a
Right.
where
Right.
the local part was
Right.
dealt with DMFT, but
Right.
the non-locality was introduced
Right.
to explain the satellite band.
Right. It's still not resolved after that debate.
Yes.
So we have not looked at that part yet.
satellite.
Yes, the satellite part. But there are a lot of claims, even for GW by GMFT. Right. So now going from antiferromagnetic to paramagnetic, you would see that if you do just a photo emission, you would not find a change in the gap a lot. But if you look at closely, there are some peaks that is kind of developing close to the valence band edge, and these are coming from the Zhang-Rai state. This Zhang-Rai state was kind of famous for the heat waves to understand. So these are bound states, and that you're going to see it in only unit orders. So you just do a photo emission measurement, you probably not going to see the change in the gap, but if you do two RPS, you're going to see some peak coming from Zhang-Rai. It can be singlet for nickel oxide, and for other cobalt oxide or iron oxide can be tablet or triplet. So this bound state that we can actually catch. So recently, actually, there was a paper on nickel oxide saying that this actually happens in the experiment, which I'm showing in the dotted line. That this valence band edge kind of sharpens when it goes from from paramagnetic to antiferromagnetic phase. That's by cooling the temperature. So which you can kind of see. And very interestingly, but recently from Brookhaven, uh, Ashish Kundu wrote to me that they are also seeing this in the RPS for manganese oxide, this these standardized states are kind of appearing in the outer. So they're kind of repeating this old experiment to see precisely and going from paramagnetic to.
If I understand correctly, the Zymerise actually appears because of the covalency with the oxygen.
Yeah, so it's a
Because
hybridized
you know,
state.
it's the hybridized state,
Right.
and you really have some kind of a ligand board.
Right.
Now, I am not very sure how exactly the magnetic state matters, except for the fact you were saying that the transition metal spins are not kind of ordered.
Right. So,
And for example, people have done this excess.
right.
They have looked at
Right.
oxygen cage
Right.
and this free peak in the
Right,
oxygen cage is
right.
a proof of that.
Right.
But if one does that excess
Yes.
in paramagnetic and antiparamagnetic,
Right. They're going to
first
see.
they are going to see some change.
Yeah, in the peak. Yeah, they're going to see the peak in the
So is it been seen other than the RTS? Is it an excess?
Yeah, this was an excess, and
This was an excess.
yeah, and this is also an excess. This was on nickel oxide.
Okay, so that's an excess.
That's an excess. So what happens? The origin is very tricky. The origin of this can be actually described in the single particle picture. So the minority spin component actually gets shorter because of the
Because the
hybridization.
covalency
The
is
hybridization.
different between two
Exactly.
pictures.
Exactly. That's the reason. And you can extend this physics even for single particle picture. Only in the paramagnetic picture or the geometric picture, this sharpening happens really large. Okay. So that's the reason. So by comparing these methods, we're actually learning physics also, which is nice. That's what we do. So next set of materials is iron-based superconductors. Their room temperature, their terminal structure, their in the normal state, they are all metals. Okay. So in the next set of materials, we investigated all these iron-based superconductors. So as I was saying, in the normal state, it is metal. If you do a simple LBA calculation, it will take only 2 minutes or so in this simple structure, FESC or something. It's going to show you metal. So is GGA, meta GGA. But if you do hybrid, which was working very well for the transition metal oxides and mod insulators, they are going to give you some insulating solution. So they are not even predicting metal for certain compounds or family. So they are not really working well for strongly correlated metals. Okay. Now, if you just compare GGA and GMFT, head to head, you see that that the band renormalizes a lot, but then overall there's a matching, but the size of the pocket changes little bit. Same as with meta GGA, here the normal pocket changes a little bit. But if you just compare with RPS, more or less all these methods are pretty good, except there is a little change in the pocket size. Okay, that matters because that also kind of tells you the pairing, but nevertheless it matches pretty well. Now, very exciting result is here. So always we look strongly corroded material. If you want to look strongly corroded material, we search this part of the periodic table. We wanted to see what happens for just for alkali and alkaline earth metal, which is a textbook example of nearly free electron system. If you open up a detail book, you see the nearly free electron system with the alkali metals. So are they correlated? So this is the question that we wanted to ask. To do DMFT first and then compared with the experiment. The experiment was done really long time ago. Again, those dots, and it matches quite well. Then we do just LDA or meta GGA. Is it overestimates the bandwidth, you can see from the experiment. And then if you do brief Philip, the hybrid, which is again working very well for the insulators, but not for the simple metal.
Actually should not be applied.
Yeah, right. Then we are going to see that if we apply other kind of hybrids, AJC is going to give the same. But right, any hybrid function should not do. GW, this was done using this 5GW code that it actually helps improving the bandwidth from LDA, but the best is actually in the NFT. Now, this was in archive in 2021, and then I saw another paper, recent paper on sodium and RPES. It was done from Germany, with the group name of the group, and then I compared. Huh? Huh? Yeah, your thing, right, your thing. Right. So then I just plotted on top of it, and you see how. Uh,
So the photon energies are different.
Uh, I mean,
The one problem with the photo emission is it's a surface sensitive.
Yeah, of course. Yeah.
Right. So if you have old data,
Right.
you have no idea.
Right, no idea. Now we have
new
better.
data
New data should help. So initially there was a lot of back-to-back URL with even JD Mahan writing saying that the RPS is not totally correct. Okay, it was back in the 90s. Now they have actually kind of saying, okay, it's not that bad from the old data, but still it overestimates the in LDA, it's overestimating the bandwidth. But it's a free electron system. If you just it should match with our test. So so there is a little bit of correlation which we can actually get it, and this is more severe problem than a gap opening up gap problem. That can be tuned, that can be cured with DFT plus C. This is kind of very fundamental problem. So
So how much error was LDA of the bandwidth?
yeah. So yeah,
You
you
are
will
showing
see.
us the dispersion.
I'm going to show. I'm going to show this error. Yes. So this was also shown in potassium also the same story. Same story. Okay. Then we did all for all our alkaline metal and compare the bandwidth with experiment available experiment at gamma. So sometimes gamma point is a little bit off from other, but we really need the whole. But still, we have no control.
So your bandwidth is the whole thing.
Yes, no, this bandwidth is just at gamma. This one on the right.
That's not true.
Yeah, but ideally we should actually compare for the, but this is how the bandwidth is like from here to here. What is the difference? So this this is how this comparison loop, and you can see that the error for bit Philip and also for hybrid, this is also for AKC, the error can go to even 80% in certain cases. 80% error. And in LDA, the error is actually close to 50%, some cases 20 to 30%. GW is within 10%, and GMF is within 5%. This the green one is the GMF. It's just for simple metal. Okay, so now we can actually think about. So we cannot spend all the materials and compare. But now we have some leading stories saying that now we can actually build the NFT data. And immediately you are going to ask me two questions, like what about the computational expense? And what about the UNJs you are fitting in the DLP? Are you going to tune it for every calculation? So the first question answer to the first question is trivial. If you just plot the scaling, it's going to scale very nicely. So if given in a big computer, you can build the data. But what about the UNG? Yes, and that has some physics problem, and we're going to see how this is done. So how these U's are computed? So let's look at the Hubbard model. And this U is actually the energy cost of a moving electron between two atoms. It's basically the difference between the ionization potential and the electron affinity. And meaning that if you have a 3D 4S kind of structure, and one can knock out one electron from D shell, put it in the S cell, and take the difference, that's ionization potential, and then in other way, you just put another one electron from S and put it in the D, that's electron affinity, and take the difference. And that's the U. So traditionally, these U's are computed using constant LDA method, and then when the occupation is constant, and the U is the second derivative of the energy with respect to the density, then it was modified with the linear response approach by Cappuccini. Then, nevertheless, you can get the U, but still is a tuning parameter and very sensitive to going from one material to another material. Then there's a constant RPA method that is actually used widely in the ethical game community. That has some extra advantages. You can get a full matrix of U, and it is also frequency dependent. Now, this is also this kind of bottlenecks for many materials where this frequency dependence is strong, and in some cases you cannot distinguish the band from correlated to uncorrelated space. So getting U is also difficult. So one example is this use in ceriums or in irons, that it depends, the value of the U, computed value of it depends, you know, on the energy window that is there. So it's not going to. So if you just use constant RPA and get the U's and you want to build a database, it's not going to work, because now you have a frequency to handle and window to handle. One material, if you want to do, yes, it's going to work, because you can compute it within the, and look at a particular energy scale where you are concentrating. But for building database, it might not work. So we are now developing this idea of constraint DMFT, where it's very similar to constraint DFT, except we now can use total energy from the DFT plus DMFT. Now it is available. So we take the three cases: you have supercell, you constrain the electron in the central cell, central atom, and then you put one electron and then take out another electron, difference C. And the good point is, in the transition metal oxide, you can take E equal to 10 volt, which is very close to what we got in all these three oxide 9.7, 9.3, and then you do paramagnetic or anti-paramagnetic calculation on nickel oxide using it is matching really well. And you just use the same 10 volt, and it's going to work. It's working very well. So that means the sensitivity is really less here, which is a good news, because I can get U equal to 10 for 3 insulator, and I can handle the issue of Q. Similarly, you can get the J.
For the RT transition, the
Yeah.
examples you are showing are all vector.
Yeah, so these are the same example I was showing for the nickel oxides or iron oxide, right? So where I do not tune, right?
All of these
Right.
are late
Yes,
transition.
right.
If you try to do it for vanadium,
Right.
only, then the problem will arise much more, the sensitivity.
Yes and no. In vanadium oxide again, it depends. So for the insulating case, you still can get very nice match equal to 10. But for the metallic case,
For example, VO2,
right,
you might
right,
in 40 years.
right.
So it undergoes a phase transition.
Yes, exactly. That's what I'm saying. Phase transition, also there is a structure of phase transition. If you think
There's a dimerization.
exactly, and that we can now get the structure from the MFT. You get the structure from the MFT, and you compute the U for these two phases. You get U equal to 10 for the insulating phase, 5 for metallic phase. So the insulating phase, you still are good with U equal to 10, even for vanadium. And that is not published yet. We're working on it, and this is how actually we can see that we can compute the U for a material, the two different phases, and then
Because the point is the spinning mechanism is very different. Both the
right,
transition.
right,
The positioning of the pores,
right,
which is empty,
right,
is very different between early transition
right,
and late transition.
right.
So I'm a bit surprised you still get equal to
Then
10 EV, even if it is insulating.
because
Probably because of the dimerization, there is something else
right,
that is happening.
the other fact is, it's a very nice one. The other fact is this fact is a very high value, so we have a very deep window, plus minus 10 from Fermi. Because of having a very big window, you get this E equal to 10. And that kind of explains that getting a big, working with a big window can solve this problem.
And here the U is put only on transition metal,
Yes.
no U on oxygen.
No. So this is like DFT plus CMMP. So everything is done on the condition method, like the impurity solver, and the things are done on the condition method
So
itself.
for you, the oxygen is not correlated at
No,
all.
no.
But they will get correlated because
Yeah,
there is a covalence.
Right, but the hybridization is going to take care of that. Because I'm using a large window, the hybridization will take care of it. That's why we get a very, even for, even for, look at this oxygen and the hybridized state. Look at with the experiment. Wonderfully matched.
Because of the large window.
Yes. That is kind of the trick here. Yes, if you ask, we have a theory, which I'm not even asking in the workshop, we do not have theory. It's kind of a work in progress. So again, for the 3D metal, we just use U equal to 5, did everything. We did not tune. We did not tune. We use U equal to 5 because if you compute for FES, it is close to 5, and we know that is going to work. Okay. So this is how we can manage. I'm not saying we have solved. We can manage building a database using DFT plus DMFT, just looking at the given set of class of material. You can compute one for you, and then it can be good for the rest. Okay, and then you can build a database. It would not be a million compound database, of course not, but at least few thousand, compounds that you can deal with. Okay.
DFT,
Yes.
similar kind of systems, people used to put like 2 or 3.
No, that exactly is the question. Is first of all the kind of, because in his case he is putting U and then treating it in a self-consistent manner
Right.
where he is using a large energy window.
Right.
So each time he actually inverts.
Exactly.
Because when he is solving the Dyson equation, he has to invert.
Right.
So the moment you are inverting, the U wherever you put,
Right.
since there is a hybridization, it's going to affect all the others.
Right.
And if you use the large energy window, then it will affect everything that is high.
That is true. Now, when I come back to the basic question of U, what is actual U?
Yeah, that's the question that actual U in which method.
Yeah.
In the DFT method, there's a different U. Then there's
Even
DFT method.
which basis you are
Yes,
working.
yeah, which method? Excellent
Because
point. Yeah, it will be good.
which
Yes.
you apply on something,
Right.
right? It's a real space concept.
Yeah.
Then in DFT, you don't have actually a real space. You have only electron density.
Right.
So you have to know on which particular site
You're going to apply.
we are going to apply. In fact, if you calculate charge with DFT,
Right.
actually there is no such thing because it's everywhere.
Right.
So then you have to partition. The partitioning is artificial. It can vary.
Right.
So you have defined whatever Pele charge.
Yeah, yeah.
No, I mean, I noticed some people use 5 over U.
Yeah, right.
3, 4, 5.
That's
So,
true.
If
that
that
is
is the
true.
case, then it makes no sense fighting over U.
Yeah.
No, fighting over you actually means that first of all the screening is very different and screening comes from all the states which are very high
Right.
energy or low.
Right.
So the problem what they fight you are saying is whether you are doing a high energy kind of physics or low energy.
Exactly.
That's
That's the point. Which scale? So it's like which scale you're looking.
You appears to be something like, as you said, cut off
Yeah.
two techniques or like that. Or physically, can one have?
no. The physically the problem is
Experimentally.
the problem is the screening.
But you
It is not a bare you. Each
Yeah,
electron
yes.
is gets
On site.
screened by your
Yeah, right. On site.
on site.
and screening and other things don't take into account.
No,
No,
screening
of course,
is
not
taken
Or
into
taken into
Yeah.
account. But
That is the main
no, usually I know that U is a function of R or like that, no, on site. Is that also correct idea?
No, that is not correct. That is all. Also, that is an approximation.
Yeah, maybe somehow ad hoc.
Yeah, it's a ad hoc.
Ad hoc way
Right.
it is coming.
Yeah, it's
Unlike
So-
long range Coulomb interaction,
Right.
which
You
is
are
real.
absolutely right that you can be long range. You can be non-local.
Yeah,
what you are
exactly.
saying. You can be
It's
frequency.
a window dependent.
Window
Very artificial way of.
Yeah, yeah.
You
Yeah,
is something you
yeah,
are trying to
but
build
this is,
from scratch.
yeah, right.
to
But this is
get-
right. But this is the LDA picture. In the DMFT picture is different because now we again the U in DFT and U in DMFT are not the same. Again, in DFT in cost can be different than in other forms because as you were saying. Again, if you take the U computed for structural parameters, not good for the spectral parameters, the spectral experimental spectral properties. So there is no universal U. But
What's good U?
yes, what's good U if you compute this, it depends on suppose you want
Only
to
to compare with
experiment.
So you have to
Yeah, experiment. Of course, again, don't forget these are all approximated methods. Okay, we are not going to solve exactly. So, how to resolve this issue? I mean, how to get rid of this issue? That is how we're going to make some progress. This is what I'm trying to say. Okay. Now the same you have used for the sodium as well, and you see that IVD, and this is all excellent math. So this is one way of tackling the U. Now I'm going to talk about. So before I go to the next phase, I'm going to conclude this part of the talk. That U's can be computed in the HT plus D and we're computing for 3D insulator, 4D insulator, 4D metal, 3D metals, and their value cluster around only a handful of values. That means it's not very sensitive, and it's not and then we using that value to compare with the programmation, and in fact programmation is remarkably close. Okay, and in all these beyond DFT methods, you can easily distinguish that DFT plus DMFT, which I'm calling just embedded DMFT, performs the best. Now you can ask this question. So all you're talking about spectral properties, what happens to the structural properties, the vibrational properties? And that is something I'm going to talk in the next few minutes. So I have 5 minutes. All right. So I'm going to talk about how we can compute electron phonon coupling using DFT plus DMFT. So whenever there is a new type of superconductors, appear, we compute electron phonon coupling using DFT. And you get a very small value. We say that it is not a phonon driven, and we throw out the phonon theory. We wanted to actually challenge this for strongly correlated compounds like iron selenide and compute this electron phonon coupling using DFT plus DMFT. Again, it is very tough because the getting force is horrible. So that time force was not actually implemented, only total energy was implemented. So we can get a band, and then we move the iron, and then we get a shift in the band structure. So that is called frozen phonon method. And those who are expert in the phonon calculation know that frozen phonon method is used in DFT to compute electron phonon coupling and dispersion. And that is what we did with DFT plus DMFT. The idea is same, but applying it for DFT plus DMFT. And what we want to get, we get a deformation potential by taking the ratio of the change in the band with the change in the ion position. And from the deformation potential, one can get electron phonon coupling. So this was done for A1G mode, and by selenium position, moving this selenium position is kind of a very interesting to see that this anion height has a very critical nature. So if you just plot the TC, measured TC, and plot it with the anion height, this is the critical phenomenon. This is a magic angle, a magic value of the height where the TC is high. Okay, and it's very surprising. And then the first thing is that we need to figure out where is the equilibrium position is sitting. So you can get it from very two different methods. And experiment is right here, and this is the plus DMFT. But experiment was kind of known. Like you can say that maybe you have to trick something to know the value. Already. Okay. Now the next step, which is quite difficult, is to get this frozen phonon, meaning you have to change those position of the atom and then keep track of the bands. And that is what I'm kind of pictorially showing here by giving a same dispersion of displacement of selenium atom of this amount and how much the bands are shifting. In this easy plot, you can see the thin plots are for DFT And for DFT plus DMFT, you see that the band dispersion is quite large, much larger, almost one order of magnitude larger than in DFT. So this is just a pictorial view. Ideally, it is done on a very large scale mesh and around the Fermi energy, and you see the shift. So, we actually found this one order of magnitude higher value, and we got excited, sent it to PRL, and then they said everything is good, but do not care phonon, okay, because this is not phonon mediated superconductor. And then the rapid communication, it appeared in rapid communication. Then I was doing something else, developing TW. By the way, this was the work that I was doing before joining Rutgers. I was collaborating with Rutgers from last 1 decade, and this was done even moving to Rutgers. So then I saw this nice experiment coming from one of the leaders in our field, the Chen from Stanford, who was kind of the inventor, I can say, of pathways, so the guru of pathways. So he has this way of directly measuring electron phonon coupling, the first way of measuring this electron phonon coupling in experiment. Previously, we have used Raman, we have used some phonon signature in the isotope effect, and etc. But now they have done exactly frozen phonon method, but in the experiment. How they have done two things together, two time domain. One is X-ray, another is R-phase. So X-ray is going to give you the position of the atom. R-phase is going to give you simultaneously the bands where it is moving. The only trick is you have to lock in to a particular mode so that really the crystal is vibrating along, say, A1G mode, and they were interested in the FM A1G mode. And you can see the black peaks which is going to oscillate the same frequency as A1G, that means you're kind of sure that it is A1G mode. Now you can actually get the band and measure the shift, and then you know how much the ions are moving and how much the bands are moving. It's very easy way I'm saying it. It's cost probably $2 million because it has to be very fast. It has to go, you have to go to synchrotron, of course. And then this is the first way of doing measuring this electron phonon coupling. They got excited. It was like scientists have seen first time dancing atom in real life. And they have in the paper, the science paper, they have actually dedicated a table comparing this equilibrium position, phonon frequency, and also most importantly the information coupling. And they have compared with our results, which was back in 2014, and you can see that the atom position, the frequency, and the deformation potential matches remarkably well in DFT plus DMFT, and it is one order of magnitude higher in DFT plus DMFT in the coupling. So this was really, I would say,
I think that's really makes sense because DFT even get the structure completely.
right.
So the deformation potential must be completely wrong in that.
Yes, absolutely. So with that, then after a few years of this experiment, there's the FEAC monolayer was discovered. And then a lot of people started talking about phonon very seriously. They were publishing in our big journals and interfacial coupling and interfacial coupling. The phonon is now kind of taken seriously in unconventional superconductors. I don't know whether it's a coincidence of that experiment, but this also shows that people are looking phonons very seriously, and a lot of papers coming. So we actually did a calculation of the phonon to understand the electronic structure for the monolayer FEAC, and we see that the system actually goes through coherence incoherence crossover instead of a mod transition. If you do a slave boson calculation, it's going to give you mod transition, which is not correct. But we see that the imaginary part of the self-energy in extrapolated to zero is going to show you the orbital dependent crossover from coherent state to incoherent state. Okay, now the most important thing is the following. Now, this is the strength of correlation, or the inverse of the strength of the correlation That means if it is larger, then it will be correlated. Smaller, some is correlated. And we have computed for bulk, monolayer just chopped out, does not exist yet in the experiment. And FAC on STO and FAC STO with the oxygen vacancy on STO. Turns out that all the orbitals kind of goes hand in hand with this angle, this FAC angle. And that is the only parameter that is going to dictate the strength of the correlation in the system. You can see that here. Oxygen vacancy is important because it gives you the right band structure of the Fermi surface because one pocket was missing. So it is donating electron to FESC and then also changes the angle just because vacancy is there. The molar, yes, that's what is surprising. It has to be because bulk you're confining now in the monolayer. Yeah, so in one direction you're cutting the hopping. Okay, but can you make a scaling or do you know without doing a calculation? The answer is no, because this is going to be dictated by this angle. So somehow this oxygen vacancy gives you a right angle, and that's magic angle 107 degree also. This is that same angle that all the PC was higher, and also makes it correlated. So now we've learned it and very seriously that the electron correlation and atomic structures are working in a feedback loop. Okay, one is controlling other is controlling this simultaneously. So this is what we have learned and we have to explore. So the other system that we have looked at after the force was done is this perovskite system. The other groups, for example, this is a flat diagram by Antoine Georges and Cyrus there. They have also seen. Yeah, it is the last slide. Yeah, so this was also shown. This kind of atomic structure and electron correlation relates to each other in other system also. So the future direction, I can say that in the past decades, we have seen that the material by designing approach in DFT. And we can say that we can design a simple material. But now we are ready to design quantum material, correlated material. That's what actually we're doing, and I'm doing in my, I started doing it in my group, that can we design superconductors using these tools? Because we're pretty good at understanding. And not only that, we can make database. Then we can also use data science tools, and that is how I hope the future is going to look like in 2 years. And also we can access the vibrational properties. So there's an announcement that I'm looking for a postdoc and also PhD student. If this excites you, please feel free to email me. The beautiful campus that we have in West Virginia, close to Pittsburgh. And in our condensed matter group, there's like quantum information experiment and also topological superconductor theorists like Tudor Stănescu is working with us, and Aldo Romero is also another expert in electron structure. And then experiments like monolayer, like STM, NBE, ORPES, simultaneously we have facility in one single room. Okay, done by Leon Lee. And then some also magnetic properties, novel magnetism that they're exploring, and optics also have a big group in exploring quantum optics. So I'd like to thank my advisor, previous advisor, Pearson College, which have been collaborating with almost 1 decade, much before going to Rutgers, and then in Rutgers, Professor David and Karen Red. And also I'm thankful to Kamal Chaudhary at NIST to help me putting up these databases, and of course, I'm thankful to all these funding agencies. All right, thank you very much.
Thank you. Questions, comments?
So I'm going to quickly tell you what is happening with the GW.
Yeah.
Why? So traditionally, this is done in the reciprocal space. Okay, this is the polarizability. This is written in this way. Okay, this is the summation of the conduction band and the valence band in the reciprocal space. Now you see this summation goes over NB and NC, number of occupied band, number of unoccupied band, right? If you look this carefully, this is just the Fourier transform. Now, if you do a standard G-space approach, the number of the Fourier transform is NV times NC because there is a summation going here and here. So, since the empty band is huge, so this number of FFTs are huge. Now, if you do this, if you compute this in the real space,
you now do partly in real.
yeah, right. This part, the polarizability part in the real space, you see that polarizability is you can just do it first with the row and the column, and that number of effects is kind of as big as your the point in the grid in the effective box, and which is about 4 times number of conduction band. Now you compare with the G space and R space, and you see that if you have a big system, if you have a small system, different.
Yeah.
But
Advantage will be.
advantage big system because that's what is lacking. You see the number of effects is at 2 order magnitude less, just using this. But this is only for the polarizability part. So that's what we get this advantage.